Hello everyone, welcome back. So we will continue from where we left off in the last lecture. So in the last lecture we discussed the PN junction in some depth. We derived expressions for the electric field, the peak electric field at the center of the depletion region. And then we also derived expressions for the built-in potential and the width of the depletion region. So I mentioned that the width of the depletion region plays a very important role because a lot of the junction physics is essentially that. Okay. So today we will try to move forward. The agenda is to discuss a few special cases. So I'll pick up problems where you have various doping profiles and we'll try to analyze what happens. We will only be applying concepts that we have already learned. We are not going to learn any new concepts right now, okay, in this lecture. So the first situation I want to discuss is a one-sided junction. I think I've mentioned this in passing in the previous lecture, but just wanted to do it here one more time just for sake of completeness. So let's say we have a semiconductor in such a way that the doping is in such a way that the ND, the N-type doping, is much larger than Na. What would you expect? Okay. So this is what is known as PN plus junction. Okay. So basically N-type doping is high. Okay. So what do you expect in that situation? So in the previous lecture we have seen that XP, the depletion region in the P region, P-type semiconductor, was equal to the N-type doping, which is Nd divided by the sum of doping, Nd plus Na, right, times the width of the depletion region. So we saw that whenever Nd was large, right, so this expression essentially becomes 1. And so if Nd was large, Xp becomes approximately equal to the width of the depletion region entirely. So what this is telling you is that the depletion region lies almost entirely in P-type semiconductor here. Okay. The same thing is actually schematically represented in this here. So you have a doping which is large, so that's why the depletion width is small here. And then doping is smaller here, so the depletion width is large. Okay. So always remember this relation will hold true. So if this, let's call it Nd, or I'll make it in small d, and this is Na. So Q times, I'm sorry, this Xn is misplaced, it should be here. Okay. So Q times NdXn Q times NaXp. The total charge should be conserved always. You know, that area, it doesn't seem so here, right? Because this is not to scale, but this area is equal to this area, always in a junction. Okay. Okay. So you could also analyze what happens when Na is much greater than Nd. Okay. This scenario is called as Na is large, so P plus N junction. So these are what are known as, again, another type of one-sided junction. So one-sided because the depletion region is going to lie in only one type of semiconductor, not the other. Okay. Whichever has a lower doping, that's where the depletion region is going to be. Okay. So essentially, I mean, you could understand intuitively also that, you know, when you have a large doping, then it will lead to excess carriers which can diffuse into the other region and then create a space charge. Okay. So yeah, this is again, so if you have a situation like this, Xn is going to be Na divided by Nd plus Na into W. So in this situation, Xn will turn out to be almost equal to W. These are what are known as one-sided junctions, and they happen often in our semiconductor devices. For example, okay, we will talk about them when we talk about MOSFETs. Okay, all right. So the next type of doping profile I wanted to introduce was linearly graded junction. You remember in the first lecture on PN junctions, I have mentioned that there are various type of junction profiles possible. because the diffusion is never going to be, abrupt, right? That's not going to be realistic. So we're going to have some profiles depending on the slope of the ND versus X. This is X on the here. So depending on how the slope is, you can have different sort of response. Okay. So this is essentially, it's depicted here. What is it? Linearly graded junction. The doping is linearly graded. So what will happen? How do we analyze this? Okay. So how is the space charge region in this case? What will happen? Please think about that. Okay. So in the previous case, it was straightforward uniform doping and then there was diffusion, right? What would happen in this case? Still, you would have the same, this is N-type region on the left side here, right? This is N-type and this is P-type. Okay, so you still have excess carriers, but at the junction you have relatively few free charges, but you still have a lot of excess on the other side in the bulk of the semiconductor. So they're going to cause some diffusion. So how will the space charge profile look like? Okay, so since there's going to be some diffusion, you can draw the space charge versus X. Okay. So how do you think the profile should be? This lecture is going to be somewhat interesting situations, interesting cases. So if you're unsure, please pause the video, think about it, come up with an answer, and then you can verify. Because in the lecture, I'll just give you the solution, but I would really encourage you to pause the video and then think about it before going ahead. Okay. So because there's going to be diffusion, some amount of free charges will move to the other side, uncovering space charge. And because the doping profile is now linearly graded, even the space charge has to be linear. Okay. So due to this is a subtle point. Please make sure that you are convinced by that. Okay. So your space charge region is going to be like this. Okay. So you're going to uncover a finite amount of space charge, and which will cause an electric field, just like in the abrupt junction case. The only subtlety here is that your space charge is going to have a shape, linear profile. Okay, that's the only subtlety. And the other interesting thing is, let's say if you call this as xn and this as minus xp, the edge of the depletion regions. What can we say about the edge of the depletion region? Is there any relation between xn and xp? Well, it's a simple linear doping, right? So there is, from symmetry, right? The doping is symmetric about the x equal to 0 point. So xn equal to xp. Okay, and if you call this entire region as depletion width, xn equal to xp equal to, each of them will be w by 2. So the depletion region is symmetrically spread. Okay, it's not one-sided or it's not non-uniform as you saw in the previous case. Okay. It's just coming because of the symmetry of the doping profile. All right, so we got the space charge, right? So to analyze any of these junctions, this is a sequence, this is a recipe we adopt. First, we look at the doping profile, we look at the diffusion, and then identify where the space charge is and what is the sign of the charge. Once we know that, we calculate the electric field and then calculate the built-in potential. That's it. Okay. So now again, what will be the direction of the electric field? Well, you have positive charge in the for x greater than 0 and negative charge in the x less than 0. So your electric field is going to be in the minus x direction. Okay. So what would be the functional form? Okay. This is where a small variation comes. In the abrupt junction case, we saw that it was like a triangular form. Electric field was triangular in the negative y-axis. Okay. It is a negative value and it's triangular in profile. What will happen here? Well, anytime we are asked to look at electric fields, we go back to the fundamentals. How did we get the electric field? We get electric field from the Gauss law, right? Gauss law turns out to be dE by dx equal to rho by epsilon silicon, right? And what is rho? Rho is now a linear function. So this is going to be Q let's say call it mx, right? Qmx divided by epsilon silicon. So this is going to be your electric field, the differential equation which will dictate your electric field. And so you can integrate this, and quickly you get E equal to Qmx square divided by epsilon silicon plus C. So note, this is an important difference from the abrupt junction. Here, E field is quadratic. Okay. In the linear, in the abrupt junction case, was linear for abrupt junction. Okay. Because there you had a uniform doping, it was linear. But now it is quadratic. Fine. But what is the constant C? What is the recipe? Okay. So this is an interesting problem for you to clear up your concepts, how we derive the expressions. So please don't get bogged down by the mathematics. Think about it from physical picture point of view, a physical point of view. Then you would clearly answer this. Okay? So electric field, can the electric field be non-zero in the quasi-neutral regions? Because outside this depletion region, it's all quasi-neutral. This is all quasi-neutral region, right? So there is no charge there. So electric field is zero there, right? And you could also think about it from the perspective of it's like a quasi-metal, right? You have lots of free charges, so they will respond in such a way that electric field will be zero. Okay, so what will be the electric field now? So since I have to make it zero at x equal to, okay, so E equal to 0 at x equal to minus w by 2 and x equal to w by 2. At both these points, it has to be 0. Okay. How do we make sure that this happens? Well, we can substitute. Since it's x square, we don't have to do much. So you substitute x equal to w by 2. So you get c equal to 0, 0 equal to qm w by 2 whole square divided by epsilon. Did I miss something? Well, I missed. There should be a 2 here, right? X square by 2, that should be, yeah. So this is equal to plus C equal to 0, right? Therefore, your electric field is going to be Qm by 2 epsilon silicon x square plus W by 2. Well, no, it should be minus W by 2. Minus W by 2 whole square. This is your electric field, right? So it's a quadratic form. You put x equal to, it works out, the conditions are satisfied, so this is it. So how does it look like? We can plot it and check it out. So let me do that. Why did it vanish? So this is x, this is E of x. Okay. And we saw that it was symmetric about x equal to 0. So it should be something of the form like this. Okay. Well, I want to do it with. Right. Okay. So this is your W by 2 minus W by 2. All right. So what happens to the potential, built-in potential, right? So let me rewrite this expression. So electric field was Qm by 2 epsilon silicon. There was a minus sign, and then x square minus W by 2 whole square. This is your electric field. What do we do for built-in potential or potential? Simply, potential is going to be V equal to minus integral of E dx, right? So we have to integrate, and we have to assume some reference for potential all the time. So assume V of minus W by 2 equal to 0. Integrate it. Okay, you're going to get some number. Okay, So, I mean, this is one of the boundary conditions, and we can say that V of W by 2 equal to V built in. So you go to the other you integrate all across the depletion region, and whatever you get is built-in potential, right? So V at W by 2 is built-in potential. Okay. So you can integrate this. I will leave it to you. Okay. So if you okay, you can essentially write this is Q m minus and minus will go. So by 2 epsilon silicon, and then x cubed by 3 minus W by 2 whole square into x plus C. This is V of x. So you have to find what is C. Okay. And then you substitute V at W by 2 and you'll get VBI. Okay. So please work it out. I mean, it's just sanity checking for you. Anyway, so, but one interesting thing that will come out is once you do all this, your VBI, sorry, not VBI, W is a width, right? So W is going to be proportional to VBI to the power of 1 over 3. You can also already see that because here you already have x cubed. So in the previous case, the width of the depletion region was proportional to the square root of voltage. Okay. But if you have a linearly graded junction, it becomes cube root and so on. Okay. So, I mean, there are more complicated profiles that researchers study because they want to look at exact analysis. But for us, I think the same recipe is used. I mean, it's just then it becomes different mathematics. That's it. There's nothing interesting about it, I would say. Okay. So, this is, I hope that, when I'm going through this, you recollect and always relate it to the what we did in the abrupt junction case. We're essentially repeating the same process, but with small changes. Okay. So this was the second case I wanted to discuss today. And then I wanted to present one more case, which is a very, very important device as far as optoelectronic applications go. It can be used in, solar cells. It can be used in, well, not so much solar cells, but photo detectors. And it's a very interesting device. Okay. So, so this case, you might not be able to get to the solution by yourself, or take your time, think about it. The problem is like this. So instead of a simple PN junction, you have a PIN junction. So what it means is you have a P-type region, you have an N-type region. Both are semi-infinite. They're extending to large. You don't large X. You don't need to worry about the length of the semiconductor. And in between them, you have a intrinsic region which is sandwiched. Okay. So this I mentioned this already in the first introductory lecture on PN junctions, and they have some profiles. Your P region has some doping density minus N naught here, and N region has a doping density. Now I just put it as 3 N naught. So some ratio you have. Okay. So how will this junction respond? Can we analyze it? Okay. So please, pause a moment, pause for some time. It might even take you, 10-15 minutes. Please take your time and then think about it. And then once you have some idea about it, and then you can always proceed. Okay? So when we want to analyze this particular device, what we need to think about is what is the condition of the intrinsic region? Okay. So intrinsic region, at equilibrium, right, has to have N equal to P equal to Ni, right? There is always this, finite number of electrons and holes produced there, right? That's the definition of intrinsic region, and that keeps, that's the definition of equilibrium, right? So, is there any excess charge or free charge or space charge? Okay. So, well, there is no excess charge, right? Because you have not doped it, so there can't be any space charge. And there's no free charge, excess free charge, because both N and P are equal. So essentially we have no excess free or space charge. Okay. It's present in intrinsic region. So what does it mean? What should happen? Right? When you have no excess charge, still there is a lot of holes. If I mention this as x naught, right? This notation is basically x naught and minus x naught, so it's symmetric about 0. So you have a lot of holes present at below minus x naught, and a lot of electrons present above x naught. So there has to be some diffusion. So there will be some holes that will come into the junction, and then uh, electrons will come in. So you'll have the same sort of physics, space charge, same sort of space charge is created, and that's why you will have some space charge here, which is positive, and this will be your xn. Okay, and on this side again you will have minus xp and negative charges. Okay, so what happens after this? Okay, the same story repeats. Now you have electric field. Of course, you're going to have electric field here all across this. Okay, so what is the functional form of electric field in the intrinsic region? Think about it. What is the electric field in intrinsic region? The governing equation for electric field is always the Gauss law, right? dE by dx equal to rho by epsilon silicon. What is rho in the intrinsic region? Rho is 0. So E field is constant. So will this constant be 0, or will it be something you have to think about? Okay, we'll come back to that. This is in the intrinsic region. So what is the E field in the extrinsic regions, N and P? Well, we can solve it. We have solved it multiple times now already. It's going to be a linear function, right? Because the doping is uniform, it's going to be a linear function. The only difference here is, remember, we still have to satisfy charge neutrality, right? Because there was no charge originally, right? Now we have some diffusion. Because of that, there is some space charge created, but still this charge neutrality should be maintained. So charge neutrality implies your p-type doping is only n naught. Okay, so xp minus x naught into n naught should be equal to xn minus x naught into 3n naught. Okay, this should be maintained. Okay. So we can quickly write the electric fields. We can write out the expressions and actually derive it. I will not do that. I'll simply show you the form of electric field. Okay. You think about the function and behavior. I'll just show you that and then see if your answer matches mine. Well, you have E of x versus x. Okay. So you have a few critical points here. So this is x naught. This is your minus x naught. This is going to be minus xp. And since the doping is high, I'll just show xn to be closer here. Okay. So the electric field outside, greater than xn and below xp have to be 0. The same situation. So we know because of Gauss law that electric field has to be this form here in the N region. Similarly, it has to be of this form in P region, right? In between them, will it come down to 0 here? Will it be here 0? Well, electric field has to be continuous. There is no reason for it to have this discontinuity, right? Because there is no charge. If there is a boundary charge, then there can be discontinuity in the electric field. Otherwise, no, right? So because of that, electric field here will be this one, constant. Okay. So this is your electric field profile in a PN junction, PIN junction. It has a lot of implications, especially in photodetectors. Okay, so you can compute. I mean, what is this relation here? this electric field expression is going to be minus. Now we should be experts in actually writing these electric field expressions. So there should be Q, there should be epsilon silicon, and then there should be the charge, right? How much is the charge here? On the n side it is 3 x n minus x naught into n naught, 3 n naught times x. Well, no, I mean this will satisfy. As x equal to, x equal to xn, it should go to 0. Okay, so I think this will satisfy it. Okay, because xn minus x naught is some number, and then x minus xn, x equal to xn, it will satisfy. Yeah, so the same thing happens on the p side. Okay, so this is how electric field behaves. I'll revisit this when we discuss photodetectors in the last 11th week of the course. Towards the end, optoelectronic devices, I'll discuss this one more time. Okay, so what is the built-in potential now? Okay, what about VBI? Well, I won't answer that question. I'll leave it to you. So it's going to be area under the curve. Okay. So what I'll do is I'll give you a brief demo of a tool on NanoHub today, and then you can try to use the tool to compute. Okay, we'll give you a problem. Consider, let's say, two devices. One, PN junction. Okay, just a simple PN junction. NA and ND are given to you. Okay, some numbers. And then two, a PIN junction. Same NA, ND. Okay, they're equal for both. So when you have that situation, I'll ask you actually to run the tool. I mean, we'll actually see what's happening anyway. So run the tool and see what happens to VPI. Okay, in both cases, built-in potential. Do you expect it to be? What do you expect about the relation between VBI? If you use both P and N dopings to be same, how will the built-in potential be for P types for the first case or second case? Okay, think about it. We will just help you run the code, and then you have to just run it once and then pick up the numbers and put it into your assignment. That's it. Okay, you don't have to solve it. Okay. All right. So I thought this was an interesting problem, and before I close, I want to show you one more interesting problem. Okay. So please don't get worried if you're not able to solve it immediately, or it will take you some time to solve it. This is, I would say, a challenging problem. But the reason I'm putting it here is to make sure that if some of you are interested in fundamentals, you could always analyze it. And if you're able to analyze this correctly, then you would understand. I would assume that you understand the junction electrostatics very well. So I mean, if it's a regular BTech or UG program, even if you don't look at this problem, I would not mind. I mean, I don't expect it out of a UG student, but I'm just including it here so that it's a good sanity check for your understanding. Okay. I have seen that UG students were able to solve this problem in the past, but out of a class of 60 or so, there might be 2 students who will solve it correctly, fully correctly. So many people would get to different levels. So yeah, don't feel too worried if you are not able to get it, but take your time and analyze this. Okay. So the problem is like this. So you have a piece of semiconductor, and then somehow there is a fixed charge in that. Okay, in this case, let's say it's a p-type semiconductor, and then somehow there is a fixed amount of charge, QP, which is inserted into the semiconductor. It can happen during a growth process. So let's say you're growing some crystal in an MBE or something. It can happen, or maybe it's exposed to some radiation, and then there is some damage to the crystal, and then there is some fixed charge at a point. Okay? This can happen experimentally also. So what happens in this scenario? How will you think about it? Okay. So I want you to really analyze this. So the moment, you see here, you have a p-type semiconductor, right? And it's symmetric about x equal to 0. So whatever is, I mean, you don't need to see any difference. And what happens if the p-type semiconductor has lots of holes, which are the free charges, right? Which are freely able to move. And you are introducing a positive charge. What would happen? the positive charge is going to repel the holes, and so you're going to have a space charge, which looks like this, right? So you have the fixed charge in the center, which is already there. It's like a delta function, right? This is going to be QP. It's like a delta function at x equal to 0. Okay, and you have the holes which are repelled on either side of the junction. So because of that, you have a space charge region here and a space charge region here. This I'll call it as xn. Well, okay, this is only p, right? So it's going to be symmetric. So it's going to be minus xp. So this is going to be negative, and this is going to be negative on both sides because holes are being repelled on both sides, right? So what will happen? Well, the charge neutrality still should be valid. So QP is going to be minus 2 times Na times Q times XP. Okay, this should be valid. Okay, and then what? See, the important thing here is should realize E is positive, right, for x greater than 0. Remember, this is positive charge, so E field direction is going to be in this direction, in the positive x direction. And for x less than 0, E field is going to be in the negative x direction. Right, x greater than 0, and this is x less than 0. So it's going to get negative for, there's going to be some sort of a jump there. Okay. And it's again a uniform doping. So you could simply write the E field. I mean, you can calculate, you can run, integrate and find out, but we know the functional form, right? Whenever you have uniform doping, your E field is going to be linear, right? And outside the depletion region, the field is 0. So here, the E field has to be this way, and here the E field is to be this way. Okay? So this I'll call as my XP, and this as minus XP. We are essentially using the same recipe as what we have seen before. Please don't get worried if you are not able to solve it by yourself. Okay? This is okay to not solve this problem fully. Okay. So E is here like this. And then what will be the, you see, what is the jump? This jump here, right? This jump in electric field is due to fixed QP. Remember always, what does Maxwell's equations tell you? I mean, Maxwell's equations tell you that there are these boundary conditions, right? And whenever there is a jump in electric field, there has to be a charge, surface charge there. In this case, since we are solving in 2 dimensions, there's going to be a line charge. Okay. So that charge causes the discontinuity in the electric field. It was not there in any of the previous scenarios that we considered. Only in this scenario you have that because of the fixed charge. All right. So then, what happens to the potential? Okay, the potential is simply going to be integral of x. Okay. So now, as you integrate it, you would see that you have to take a boundary condition, right? So of course, the same as usual, I'll take v of minus xp equal to 0 and v of xp equal to vbi. Okay. So please integrate it. You will see that since its electric field is linear, this is going to be quadratic, and the built-in potential is going to be x, v of x, and the built-in potential is going to be something like this. Okay. This is minus xp and this is xp. So at x equal to xp, this vbi is 0 in this case. There is no built-in potential as such. Okay. But there is an electric field that forms in the depletion region. Okay. So this problem might be a little challenging. I don't expect any regular undergraduate student to really solve it. But if you're somebody that is interested in understanding the device physics in depth, this would be a useful thing. Okay. So with that, now if you're able to solve it fully, I'm sure that you have a very good hang of electrostatics of PN junctions. Okay. So with that, I would like to stop today. I'll just also add a brief demo of the NanoHub tutorial that I mentioned, NanoHub tool that I mentioned. And then in the next week, we'll start analyzing what happens with uh, applied voltages. So far, we have not applied voltages to the junction. So we will start applying voltages and see what happens to the current. Okay. All right. Thank you so much for your attention. I'll see you in the next week.